Okay, this is for topic 5.1, reaction rates, and our objective is we want to be able to use a balanced equation to state our reaction rates. Now, one thing to consider is that these rates are come from experiments where you'd have to measure how concentration changes over time. And here you've got a, excuse me, a bone arrow flask, and you've got the tubing, and you've got a gas syringe where the gas is going to fill up the syringe, cause the syringe to get bigger. And then you can measure the volume and be like, okay, how did it concentrate? This would be the concentration of the reactant. In this case, it would go down, and the concentration of the gas would go up because you're making that. All right. So these rates that we're going to talk about, they're done measured experimentally. And that's where they come from, studying reactions. All right. Now, this is a branch of kinetics. All right. Kinetics really wants to understand why these reactions occur at the rate that they do and what affects what how to influence it. All right. So that's kinetics. All right. And here is your definition of a reaction rate. You want it's much like a or like a speed, where speed is distance over time, or this is a concentration time, right? We're going to use stoichiometry, as it says. All right, these are its units. You want some sort of constant. Often it's molarity divided by time. All right, and we're going to tip, as it says, positive. In general, it may be understood that something's going to be disappearing, but it's still going to be a positive value typically. All right, so here's an equation. It's got three chemicals in it. All right, we've got A, B, and C. For chemical A, what's its rate going to be? All right. Well, much like this speed is distance over time, rates are going to be a brackets with this delta. All right, and that is change in the concentration of A. Now I'm giving it a negative value because uh, it's turning into the products. All right, so its disappearance per unit time would be its rate, and it's negative. The reason it's negative is so that when we compare them, they're going to be equal. Now, with chemical B is going to be basically similar, chemical B's rate, except that we're going to change the top factor and make it delta B. Remember, delta means change, like initial or final minus initial, for all of these. And C is going to be similar, and it's also going to be an appearance. Now, to see how these things are related, um, you're going to need to look at the things in front, the coefficients. I hadn't thought of what it was. Coefficients for the balance equation. You can see A is 1, B is 3, and C is 2. That means is whatever their rates are, they're going to be proportional to each other, just like the molar ratios. A's rate is its disappearance is uh, 3 times that, or a third of what B's appearance rate is, and half of what C's appearance rate is, because of the molar coefficients. All right. So A's disappearance rate is equal to a third of whatever B's is, and half whatever C's is, and that's the relationship. And one last thing to consider is they're gonna these graphs. Well, since A is disappearing and B are appearing, that's how they're going to look in general. And C is going to, I didn't get this C perfectly curved, but C is going to appear at a higher, oh, I got that backwards. This is B and this is C, sorry. B would appear at a higher rate because it has a bigger coefficient than C. So B would come at a higher rate, this one, then this is C, and this is A. All right? Thank you, and I hope you have a good day or good night.